We have finally made it to the last topic you guys need to know from this unit that I feel like we've been in for like 5 years. And the final topic that you need to know are these tests for symmetry. Now, I've spent a lot of time having you guys look at the symmetry of graphs. So we've talked about the three different types of symmetry for polar graphs. The first type of symmetry is about the x-axis. Keep in mind, I've been calling that the polar axis, or I've also called that theta equals 0. So all three of those things are talking about the same idea, this x-axis, and I will highlight that line because example 1 down here is going to show you what that means. So when you have this symmetry about the x-axis, you're going to see that mirrored image over the x-axis. Now, in order to find the symmetry over the x-axis, or verify that a function has this symmetry with the x-axis, there's actually two different symmetry tests that you can use. The problem with these symmetry tests is that sometimes you'll use the first test, which I like to call plan A. So you guys are going to hear me say plan A, plan B. The first test I like to call plan A. Sometimes is inconclusive. So it will have, the graph you will know has this type of symmetry, but you use this symmetry test and it'll be inconclusive. It won't verify it with this first test. So if the first test doesn't work, you have to resort to plan B in order to confirm that symmetry. So it's a little tricky. It's a unique topic, but I'll show you how this works momentarily. Just to show you why plan A versus plan B will work for the symmetry with the x-axis is if you think about a point r comma theta. If you have this symmetry with the x-axis, keep in mind that there's two other ways you can represent the point that is the reflection point. The first way is this idea of r with the opposite of theta. So think about if your angle was 30 degrees and I just make that angle negative 30 degrees, but then keep the r value positive. Note that that's going to be the same a representation for that reflection point. But there's another way you can represent that reflection point. If you think about what this is saying, and actually in the second image, it shows this idea of r comma pi minus theta. But if you think about theta being in the first quadrant, so let's just say theta's 30 degrees. If you want to get the angle in the second quadrant, so this angle over here, keep in mind if this was 30, this angle right here would be this pi minus theta, or in the case of 30 degrees, it would be 150 degrees. But note, that would take you to this point right here. We want to land at this point right here. So you can change your theta to pi minus theta, but then you would have to switch your r value to get this point that we want as that reflection point. So it's a little tricky. I know that might be a lot to digest right now, but just note that these are two different ways you can confirm something has symmetry with the x-axis. Now, the second type of symmetry we're going to talk about, which you guys have been seeing in these graphs, is about the y-axis. Remember that this is when I say let's not use a highlighter, theta equals pi over 2. So it's symmetry over that line, which is also called that y-axis. So again, we have the plan A and then the plan B. For the plan A, you will see why, and again, going back to this like pi minus theta, if I give you some point and you want to have this symmetry with the y-axis, think about how we have to be that same distance away from the y-axis. So when you're thinking about the actual opposite side of this, you're really thinking about that angle's supplement. So we're going to take that pi minus the theta that you have. But then because we are keeping and we're going towards that angle, you would keep that r value positive. Now, if you note, you can also take the opposite r value with the opposite theta, because remember, if you go to the opposite theta, you're talking about going here. But remember, we don't want this point here. We want this point here. So what you could do is you could change the R value and then you would land there. So that's where that second way of doing this is. So those two different ways is you can just take the opposite angle and then just change your R value and you'll land at that point. Or as I said, the other way, you can think about that angle supplement and then from there keep the R value the same. The third type of symmetry that we've looked at is the symmetry about the origin, or remember we call that rotational symmetry. So that 180 degree rotational symmetry with the pole. Both mean the same thing. So you guys are going to see, I think that with the origin, this one like just connects with me a lot faster than the other two. It makes sense. And I think this really goes back to our polar graphing when we were doing the graphing of points. And I said, find other ways to represent this ordered pair. Well, think about if something has symmetry with the origin. We're talking about this like reflection over the origin, if you think about it. So note that if you want a point that is on the over that reflection point. So if you want to represent this point in two different ways, think about how you can keep the angle the same, but then go to the opposite R value. So remember that if you said 30 degrees, but now change the R value to -2, it would take you to the point over here. So that would be your plan A. And then plan B, again, should make sense because based on graphing, remember to get to the opposite side, we can also just take that theta and add pi, but then keep the R value positive in that scenario, because once you add your theta to pi, you're going to be on that opposite side and you want to go towards that angle to get to that highlighted point right there. So I know that's a lot to digest. You may even have to watch this part of the video again just to kind of really wrap your head around that. But those are the three different types of symmetry that we've talked about and the two different tests that you can do for each type. So unfortunately, that's heavy enough, but you also are going to see the identities that we talked about earlier on come back into this. And that has to do with that Plan B test. Because this Plan B test has the pi minus theta, we have the difference and sum. You're going to see that those sum and difference formulas can come back into play. And then understanding the idea of even odd identities is going to really be because of the Plan A formulas. So just kind of keep in mind that the Plan B formulas are where you're really using these identities. And then the even odd identities you're going to have to think about for Plan A. So I wanted to make sure these identities were there for you so you can refer to them easily. So how is this done? We only have 2 questions to look at, which usually in math is a bad thing. When it's only 2 questions, you know it can be a little bit of work. So what I always suggest doing with these is think about the graph first. You don't have to show and confirm all of these different things because remember, some of these graphs have only one type of symmetry. So with this first one, I know right away that this is going to be a limacone, and this limacone will have an inner loop because the ratio of A to B is less than 1. Now, with that being said, because it's sine, I know that my symmetry is going to be with that y-axis. If you guys remember all the ones that we've done with sine, you would see that it's being cut by that y-axis, unless it's like the lemniscates that get rotated, but those don't show that symmetry. Now, if you want to confirm that, obviously you can take out your graphing calculator. Actually, you know what? I'm going to use Desmos. I love Desmos. I think Desmos shows these graphs so well, but just to see it visually first, I think is really important. So what you can do is you can change your grid to that polar grid, and then you can do the R equals, and then the 1 minus 3, and then we can go to our functions, sine, and then we can get our theta, and ooh, rho. We can distort the image a little bit, but what you'll see is that this does in fact have symmetry with the y-axis. Now, that's not the notes for today because we've already talked about how to look at a graph and determine the symmetry. What you need to do now is prove this algebraically. So what we're going to do is use Plan A, and if Plan A doesn't work, Plan B with our symmetry tests. So notice with the y-axis, plan A is what we're going to do is sub in the opposite r and the opposite theta. So that means, and I'll write that down, opposite r, opposite theta. When we sub this in, we should sub in, so let me put steps. So these are your steps. Step 1, you sub in the opposite r and the opposite theta. Step 2, you simplify. And step 3, you check for the identical equation. You confirm symmetry, and maybe you remember doing this in the beginning of the year with even and odd functions. When we sub in the opposite theta, do we get the exact equation? Do we get the opposite equation? You want the identical equation in order to confirm that this is the correct symmetry, which we know it is. So let's see how this works. You're going to take the original equation, and everywhere there's an r, make it the opposite of r. And then everywhere there's a theta, you're going to fill in the opposite of theta. Now, from here, you are going to look, why does my thing always freeze? It's something to do with Desmos, I swear. You're going to look at the even, odd identities. So when you look at your even, odd identities, should I just do this without? You're going to remember that if you were to graph a sine function, remember it starts at the origin, and then to the right it would go up, to the left it goes down. It's an odd function. Remember that the opposite angle, which is what this says, negative theta is the opposite angle, produces the opposite value. So with that being said, when we use the even, odd identities, you can actually scroll up in your sheet and see this. The sine of opposite of theta is actually equivalent to the opposite sine theta. Now, once you replace that using the odd identity, you can actually then multiply and get this 1 plus 3 sine theta. See that negative on the other side? We can now divide by that negative and check to see if we get the same exact equation. But here's the problem. Plan A didn't work. This right here, and let me just cancel this out. I'm sorry, I'm gonna have to open this back up for you guys. Plan A does not work. It's inconclusive because if you notice on your notes, which didn't freeze, we didn't get the same exact equation. So unfortunately, when you don't get the same exact equation, we say that this test was inconclusive. Okay, I guess now I can't write. Let's try this one more time. These videos have gotten really entertaining, am I right? So please let me have a pen. Okay, there we go. So inconclusive for this one. Now, if plan A does not work, you have to do plan B. So going to plan B, so this was plan A, you basically are going to do the same steps, but now instead of subbing in the opposite r with the opposite theta, you are going to do plan B test where you're going to keep r the same, but for theta, you're going to sub in pi minus theta. So we're going to keep r the same, but we're going to sub in pi minus theta. So let's do this again. So I will put a line down the middle. Plan B. Here we go. So going back to the original equation, we're going to keep r the same, and then I'm going to replace the sine theta with the sine pi minus theta. Now I can scroll up because I'm not frozen. You can use the sum and difference identities. Notice this is the sine with a difference. So you're going to be using this formula here in order to simplify this. So if I am going to use that formula there, 1 minus 3, remember that we're going to get the sine theta, and by theta I mean pi, cosine theta. Sine, same sign, so that's going to stay as minus, and then the cosine pi times the sine theta. Now, sine theta, unit circle, is equal to 0. cosine theta unit circle is equal to -1. So if you simplify what's in the parentheses, note that this whole first part goes away because it's getting multiplied with 0, but then you're going to get a minus -1 times sine theta. You get a positive sine theta from all of that. Wham, bam, thank you, ma'am. You guys are going to notice that the symmetry has been confirmed. And how did I know that? Because when I look at what I got here, it is the same thing as what I started with there. So plan A failed us, but plan B helped to show that this is in fact symmetric with that y-axis. So woo, that was a problem. One more problem to look at, and then that is it for the notes for today. Let me make this small. All right, here we go. So for this next one, feel free to graph it. Hopefully you recognize that this right here is a rose. The petal length is 5, and because this is even, it's going to have 4 petals. Because this is cosine, what you're going to see is that each of those petals are going to fall on an axis. So it would look something like this. Ooh. There we go. This has not just one type of symmetry, not 2 types. This actually has all 3 types. So, wowzas. So let's look at how we would confirm the symmetry, and I'll use different colors for this. So starting with symmetry with the x-axis, we're going to use the plan A test, and we're going to try to sub in r with the opposite of theta and see if that works for us. So let's start x-axis, and we're going to sub in r with the opposite of theta. And again, we're checking to see if we get that same exact equation. So I'm going to keep my r the same, and then for theta, I'm going to sub in, actually, that's okay, the opposite of theta. I guess I didn't really need a parentheses there. Now, go to your even odd identities. You should remember that cosine is an even function. So if I were to keep graphing this, the opposite angle produces the same exact y value. So this is very strange, but what that means is that this whole thing is just equivalent to the cosine to theta. And then with that 5 in front, you'll notice that this produces the equivalent equation. So in this case, plan A is our jam. Plan A worked for this. Cha-ching. I don't know why cha-ching felt necessary there. I wish this video wasn't so long because I would like unrecord that. Anyway, let's talk about that y-axis. So going to the symmetry for the y-axis, if you guys remember from the last problem, we want to sub in the opposite r with the opposite theta. So what we can do is we can sub in the opposite r with the opposite theta. So what we end up getting is the opposite r equals 5 cosine, and then 2 times the opposite theta. Now, again, for the same reasons from up above, this whole thing is going to become the cosine to theta. Okay, because it's that even function, so those two would be equivalent. We're going to have that 5 in the front, and then we're going to have over here the opposite r. Now, if you divide the negative, you're going to get r equals -5 cosine to theta. Now, unfortunately, if you look at this, you're going to see that this is not the same exact equation from up above. So unfortunately, we're seeing that this plan A is inconclusive in this problem. So then what we could do is we could go to that plan B. So when we go to that plan B, like we had done before, we are going to sub in the, as we had done over here, we're going to sub in the r with theta minus pi. Pi minus theta. I don't know why I keep doing that. So we're going to have r equals 5 cosine 2, and then times this pi minus theta. Now, before you actually use the difference identity, you can distribute that 2 pi minus 2 theta. and then make this like your first angle, this your alpha, this your beta. So when we use the difference formula for cosine, we're going to get cosine, I'll put this in like a bracket, 2 theta times cosine 2, did I do it again? Oh my gosh. 2 pi times cosine 2 theta. Sorry about that. I know this is getting rough. Cosine changes. Then we get sine 2 pi times sine 2 theta. Was okay there. If you go to 2 pi, the cosine there is 1. If you go to 2 pi, the sine there is 0. So what you'll see is that this goes away right there. And then what we have is this r equals 5 cosine 2 theta. Should I do the cha-ching? You will see that that is the same thing as the original problem. So what we're seeing is that this is conclusive, so symmetry has been confirmed. All right, now final thing is with the origin. So for this one, we had plan B that worked. So if you're still listening, thank you for sticking because I know this problem is epic. Final thing that we are going to look at now is the origin. So with the origin, if you remember, or if you don't, just go back up to the top. To do the origin symmetry, we're going to sub in the opposite r and keep theta the same. So our plan A would be the opposite r, but keep theta the same. So here we can sub in that opposite r. So we're going to do negative r equals 5 cosine 2 theta. And then we're going to be in that situation, negative 5 cosine 2 theta. So we can do the other test here with the origin. And so with the origin, we have that other test where we're going to keep r the same, but then we're going to do pi theta plus pi. So our plan B, as I just said, is we're going to keep r the same. So, and then we're going to do the theta plus pi. So keeping r the same, we have r equals, and then we have the 5 cosine of 2 times theta plus pi. So again, we can distribute 2 theta plus 2 pi. You have your alpha and your beta. So we can rewrite this as 5, and then brackets or parentheses is fine. Cosine 2 theta times cosine 2 pi. Cosine changes, sine 2 theta times sine 2 pi. So cosine 2 pi, if you recall, is 1. Sine 2 pi, 0. So what we end up getting is 5 cosine 2 theta, and that confirms our symmetry. So thanks for sticking with me. If you are still listening, is anyone out there? Am I alone? But I hope that that helps you with those symmetry tests. I'm also going to be posting an additional document that is helpful. If this did not make sense, you can go through and look through that document.